Hey everybody, today's video is just going to be a quick exploration of Fibonacci numbers in Python. And what I'm going to show you is how the closed form of the Fibonacci sequence calculation uh, pretty quickly runs into rounding errors. And this has to do with how fast the Fibonacci numbers grow. Quick review of what the Fibonacci sequence is. You start with the numbers 0 and 1. You add those together to get 1. You add 1 and 1 to get 2. 1 and 2 to get 3. Um, and there's a great article on Wikipedia about this. This sequence was originally studied in terms of studying the population of rabbits, which is kind of fun. But it's basically an exponential sequence that's not like entirely obviously exponential. At least not. It's not literally taking the exponent of a number, but it grows in an exponential fashion. And sometime during the 1800s, French mathematician named Jacques-Philippe Marie Binet, which I can't think of a more French name than that, discovered this closed formula for it. And apparently it was already known by Demoivre and Brunelli, so French and Swiss mathematicians. Um, if you go, if you search for like closed form Fibonacci, or if you search on YouTube for like Binet's formula, you can see how this is derived, and there's some pretty interesting mathematics. It's obviously not trivial since it was only discovered in the last couple hundred years, but it is understandable if you have a decent like college math foundation. But anyway, I was curious to see in Python like how quickly do I get to large enough Fibonacci numbers that the closed form of the Fibonacci sequence calculation, how quickly does that run into floating point errors? So this is, as you can see, it's a 32 line program. This is the Vim editor, if that matters. I have this root 5 constant, which is just the square root of 5. And then I have phi and psi, and I will let you read the Fibonacci, the Wikipedia Fibonacci article to get a little more detail on that. But all I'm doing is transcribing that mathematical formula from Wikipedia into Python in this closed fib. And then in my test function, all I'm doing is creating a dictionary of Fibonacci numbers in terms of integers. And here I'm using what you saw in the earlier page, where I'm literally generating the Fibonacci numbers along the same lines as if you did it by hand. Some of us, I think, learned this sequence as early as elementary school, but certainly by high school, I think most people encounter it, even if it's just kind of as, an oddity or whatever. But in Python, I'm literally just going through a loop from 2 to 100, and I compute the value of the ith Fibonacci as the sum of the prior one and then the penultimate one, the one that's prior to that. And then I print out the value from the integer calculation, and then I print out the value from the closed fib calculation, which is essentially is using floating point arithmetic. And as soon as I encounter a situation where the values don't match, and I'm just using int to round off of floats, then I print out a rounding error. And with no further ado, I will just run the program. And you can see that it only takes me going up to the 72nd Fibonacci number to encounter a rounding error. It's pretty impressive how well this formula works. Like Fibonacci of 66, when you do those integer calculations iteratively, essentially 66 times, maybe you call it 65 times, since the first couple values are hard-coded. That leaves you with the exact same result as when you use that exponential formula from Binet, Demoivre, and Bernoulli over here. But you do eventually encounter rounding error, and you can see that the integer calculation here is this long number 498454011879264. The last digit is 4, and that integer arithmetic makes sense because if you look at the last digit of the prior one, it's 9. The one prior to that is 5. 9 plus 5 is 14, so it makes sense that the integer value does end in 4. And I trust the integer calculation because I know that Python has big integers, basically unbounded integers. And how Python does that is a little out of the scope of this video. But you do get a rounding error, and the thing to notice here is the closed fib of 72 has about 48 bits. And in order to calculate that it's about 48 bits, I just use math.log with a logarithm base of 2, and that tells me that the final result of closed fib has about 48 bits. Now, that doesn't tell the whole story of why you're having this floating point precision. It's just interesting to me that it's like in the ballpark of 64 bits. So if you know anything about kind of like how floating point arithmetic happens, you would expect at least that order of magnitude. So that's pretty much it for this video. What I want to do in a subsequent video is see if I can use the Binet formula in a little more, or at least for bigger values. In order to do that, there are several strategies. I could try to like simulate floating point arithmetic myself. I could try to find a library that does higher precision floating point arithmetic, or maybe there's a better idea that I haven't thought of. And of course, if you have a good idea, please put it in the comments. But anyway, I hope you enjoyed that. That's it for now. Goodbye.